All right, welcome to the explainer. You know, if you've ever seen a CT scan, you've witnessed something pretty amazing. A super detailed 3D image that's literally built from nothing more than a bunch of X-ray shadows. So today, we're going to pull back the curtain and look at the incredible math and, really, the magic that turns those faint shadows into clear, life-saving images.
Okay, so this is the central question, right? How in the world do we take a whole bunch of simple, flat, shadowy pictures from all these different angles and then somehow mathematically turn them into this incredibly detailed 3D reality of what's inside? It's a puzzle that's, part physics, part computer science, and honestly, a little bit of pure genius. Now, to get to the answer, we've actually got to go back in time. I mean, way back, long before anyone even dreamed of a CT scanner. The solution was already there, kind of hiding in plain sight in the world of pure math. It was this absolutely brilliant solution, just waiting for a problem to come along. So picture this. It's 1917. An Austrian mathematician named Johann Radon comes up with this thing called the Radon transform. And he had no idea, no way of knowing he was laying the groundwork for a revolution in medicine. But he proved, mathematically, that if you had all the possible projections through an object, think of them as line measurements, you could perfectly, and I mean perfectly, reconstruct what that object looked like on the inside. But for decades, this was just a cool math problem, a curiosity. And this is where all that abstract math smacks right into the real world. As a CT scanner spins around, it's collecting all of that projection data, and it organizes it into this thing called a sinogram. I know, it might look like a piece of abstract art or something, but trust me, that pattern is everything. That right there is the real-world Radon transform, the very thing Radon was just dreaming about on paper.
Okay, probably the easiest way to wrap your head around this is to think of a Sudoku puzzle. The sinogram is kind of like getting the sum totals for every single row and every single column, all at once. What Radon proved, and this was his genius move, was that if you have all of those totals, you have all the clues you need to work backwards and figure out the value of every single little box. And boom, that's your final image.
Okay, let's fast forward to the 1970s. We've got the theory, right? But now the first actual CT scanners are being built, and the engineers have a problem. They need a fast, practical way to do this whole Radon thing in reverse. And the answer they came up with was this super elegant and computationally smart algorithm that became the absolute workhorse of the industry, filtered back projection, or FBP.
So the first step is just called back projection. And honestly, the idea is wonderfully simple. The algorithm takes each of those individual X-ray profiles and it smears it back across the image, right from the angle it was taken. Really, think of a painter using a super broad brush, just swiping layers of paint onto a canvas from all different sides.
But there's a huge problem. This simple smearing technique, it creates a blurry, out-of-focus mess. You get these classic star-like artifacts all over the place. The smearing process itself just fundamentally blurs everything. So yeah, it's a start, but it's absolutely not the sharp, clear image a doctor needs to make a diagnosis. Not even close. And this is where the filtered part of filtered back projection comes in. This is the secret sauce. To fix that awful blur, the algorithm does something really clever. Before it does any of the smearing, it applies a special mathematical filter, basically a sharpening filter, to each and every projection. By sharpening the data first, it perfectly cancels out the blur that the back projection step is about to create. It's an absolutely ingenious fix, and it makes all the difference in the world.
And for decades, this method, FBP, was the absolute king. Its biggest pro, speed. It was incredibly fast and pretty easy on the computers of the time, which was huge. But it wasn't perfect. The big trade-off is that the same sharpening filter that gets rid of the blur, it also makes any random noise in the data way worse, so you can end up with grainy images. And it really struggles with things like metal implants, which create these big, ugly streaks across the picture. But of course, the world kept pushing for better, clearer images, and maybe even more importantly, for ways to get those images with less radiation dose to the patient. So science had to move beyond FBP. We needed a totally new way of thinking. And instead of FBP's one-shot direct calculation, this new approach is, it's more like a conversation, a back-and-forth process of making things better and better.
And this is called Iterative Reconstruction. So here's the big idea. It starts with just a rough guess of what the final image might look like. Then it does a virtual CT scan on its own guess to create a fake sinogram. Then it says, okay, how does my fake one compare to the real one we actually measured? It looks at all the differences, all the errors, and uses that information to go back and fix its initial guess. And it just keeps doing that loop. Compare, correct, update. Compare, correct, update. Getting a little bit closer to the perfect image every single time.
Now, this whole process brings up a really fascinating challenge. You're essentially trying to tell an algorithm to do two things that are complete opposites. It's like saying, hey, go ahead and smooth out all this grainy noise over here, but whatever you do, don't you dare touch that super sharp edge right next to it, because that's a critical detail. How do you program that?
Well, the answer is a brilliant mathematical technique called total variation regularization, or TV for short. And the way it works is just so cool. It tells the computer to think of the image as a 3D landscape. All the random noise, that's like bumpy, hilly terrain. But the real, important details, those are like sharp, steep cliffs. TV regularization basically tells the algorithm, your job is to make this whole landscape as smooth as possible. Flatten out all those annoying little bumps, but you are not allowed to mess with the cliffs. It's a fantastic way to kill the noise while keeping the details. So, this brings us to the big trade-off, right? On the one hand, these iterative methods give you absolutely superior image quality with way less noise. And that is a total game changer for lowering the radiation dose for patients. The catch? All of those loops, all of that comparing and correcting, it takes a ton of computing power. It's just way, way slower than FBP. And to be fair, some of the early versions got a bit of a reputation for making images look a little unnatural or plasticky. But the newer algorithms have gotten much better at that. So, okay, we've got these incredibly powerful algorithms. How do people actually use them? Well, it really boils down to who you are and what you're trying to do. Are you, say, a technician in a hospital who just needs a perfect, reliable result, like right now? Or are you a scientist in a lab trying to invent the next big thing? And that leads to two completely different philosophies. First, you've got the commercial vendors, what we call the black box. This is a perfect, validated, turnkey solution. You're not supposed to mess with the insides. You just pick a setting, like reduce metal artifacts, you push the button, and you get a beautiful, reliable result every single time. Then, you've got the complete opposite, the open source glass box. This is a playground for scientists. It gives them all the building blocks, all the individual pieces, so they can tinker, experiment, and build totally new algorithms from the ground up. And that really brings our whole journey here full circle, doesn't it? We've gone from pure abstract math scribbled on a piece of paper over 100 years ago all the way to the absolute cutting edge of what's possible today. And believe me, this story is not over yet.
I mean, you can really see the whole history laid out right here. It all started with the theory from Radon back in 1917. Then in the 70s, we got the workhorse filtered back projection that made it all possible. The 2000s brought the refinement with smarter iterative methods. And now, today, we are standing on the edge of the next great leap forward, AI and deep learning.
So as we wrap this up, let's just leave it with this one thought. This entire story, from start to finish, has been about one thing, a relentless quest to see the unseen, to turn simple shadows into real substance. And now, with AI and deep learning entering the picture, promising to create these images faster and with better quality than we ever thought possible, the question isn't just about what's inside an object anymore. The real question is, what impossible things are we going to see next?